Jeff Lundeen, our CAP speaker. Jeff is a new faculty member at U Ottawa, and just here's a little brief bio, and I'm sure you can fill in the rest. Jeff did his undergrad at Queen's in physics, his grad work at University of Toronto, then was a postdoc at Oxford and has been at the NRC the last few years, and I guess just started here last semester? July, yeah. Okay, and actively looking for students, so graduate students. So if you're interested, I'm sure he'd be willing to talk to you, and I'll let you.
Thank you. So this is supposed to be a talk that's part of the undergraduate CAP lecture tour. So CAP is the Canadian Association of Physicists. So I'm supposed to say a few words about them before I start my talk. So it's the association that represents physicists in Canada. There's 1,600 members. It puts out a journal called Physics in Canada. I meant to bring it today because it's actually quite a good journal to read because it gives you introductions to subjects. So for instance, this month is a really great introduction to particle physics, the state of particle physics, and there's some fantastic articles in it. And you should all join, particularly if you're undergrads, because if you're undergrads, it's free. So there's really no drawback in joining. And if you're a grad student, it's free for the first year, and then it's really cheap for the subsequent years. Some of the other things that the Canadian Association of Physicists do are organize the annual CAP Congress, which this year is in Sudbury at Laurentian University. And then also they help support the Canadian Undergraduate Physics Conference. So I helped organize that when I was an undergrad at Queen's, and it's a really great thing to do. You get to meet students from all over the country. And people are very willing to give talks at it. So for instance, at the year that we did it, we asked Bill Phillips to give a talk. And he had just won the Nobel Prize a couple months before, and he came and gave a talk. So it gives you shows you what kind of pull and how people treat these type of undergraduate conferences. Okay, so that ends my sales pitch, and now I got to get out of this. Go on to my little presentation. How many people here are undergrads? Put up your hands. Oh, that's great. Okay, good. So this talk is it's supposed to be at an undergrad level, which probably means it's not at an undergrad level, it's at too high a level, but it's probably then appropriate for everybody else, whereas most colloquia are pitched at too high level. So the second half of this talk is going to be about this experiment that I did while I was at NRC, where we directly measured the wave function. It was published in Nature in 2011, and it got a fair amount of press, including it was selected by the editors of Physics World, which is the magazine of the UK Institute of Physics, our counterpart to the CAP, as the #2 breakthrough of 2011. So I'm going to tell you about that in the second part of the talk. Let me just try and get this working. Oh, that's the symbol I want to see, right? Okay, I'm not quite sure what's going on there. I just tested this. Okay. Okay. So that's going to be the second part of my talk. The first part of my talk, I'm going to introduce the wave function because this is an undergrad talk. I'm going to start out very basically and then slowly go through what we've learned over the years about the wave function and some of the arguments that there have been about it. And then finally I'm going to end up with our contribution to the argument, which is how we directly measure the wave function, and talk about an experiment where we do so. But in that experiment we did not do so with a hammer. This is Alan Migdal, a somewhat famous quantum optics person, showing us how to do experiments at NRC. You do not do them with hammers. Okay, so the wave in classical physics, a particle has a particular position and momentum, and that completely describes its state. The Heisenberg uncertainty principle implies that this is not possible. So a particle has a certain range of positions and momentums according to the Heisenberg uncertainty principle, and neither of them can be a single value at the same time. So instead, in quantum physics, a particle is associated with a distribution of positions and momenta, a complex distribution known as the wave function. So if you haven't seen the wave function yet, like if you're in first year, you probably did see it in high school when you were introduced to orbitals in chemistry. So the orbitals of atoms are wave functions. So these are the orbitals of the hydrogen atom. And the wave function was introduced along with the Schrodinger equation, introduced by Schrodinger at the beginning of the century. And the Schrodinger equation tells us how the wave function evolves in time. So it's like Newton's laws for classical physics. And it's the basis of most modern physics, and people love it, including this person here, who I assume was a grad student who got it tattooed on her back. So that's, I think that's actually not too bad. It's kind of tasteful, but this guy thinks it's good. So we love the Schrodinger equation, and we love the wave function in modern physics. Now, we use the wave function to make probabilistic predictions. So that's one of the main weird things about it, is that it's probabilistic. And one of the first things you learn to do is calculate the probability of finding a particle at a particular position, where you just take the absolute square of the wave function. But in fact, you can do something similar to predict the probability of anything measurable, anything possible measurable. And that's known as the Born rule. So for instance, you could predict the probability of finding a particular energy, or the average energy, or a particular momentum, or anything else that's possible to observe. So that's how we use the wave function. So in classical physics, a particle is described by a particular position momentum at any time, and then from that time on, you can use Newton's laws to propagate it in time and find out exactly where it is. So it's completely deterministic. So our counterpart in quantum physics is that we have this wave function that now has some spread to it. It's not got a single position or momentum. And most of the time it does what we see in classical physics. So it bounces back and forth in a well, just like the classical particle. But sometimes it doesn't. So for instance, if we have a barrier in classical physics, a particle will bounce off of it. In quantum physics, there's some possibility, you can't really see it very well here, but there's a very light block going this way, that the particle will tunnel through the barrier. So some phenomena happen in quantum physics that don't happen in classical physics. And one of the weirdest phenomena that doesn't happen in classical physics is the wave and particle-like behavior exhibited by the wave function itself. So the wave function has a phase, just like a wave does. And in fact, you can think of it in some ways like a wave. So the classic Young's double slit experiment, we have a particle or a photon or an electron coming along, and it hits the two slits and it diffracts out to create these circular waves, and they interfere to give these bright fringes here. And now the weird thing is that although we think of most waves, like water waves, as having many particles in them, this occurs for a single particle at a time. So if we let just one particle through the system, we'll still see this interference pattern slowly build up on the screen on the far side. So we see this wave and particle-like behavior at the same time, in some sense, in quantum mechanics. And it's important to note that it's not just the magnitude of the wave function that matters, it's its phase. So the phase, if you shifted the phase, would shift the position of these fringes back and forth. So it shifts our predictions that we get from the wave function. So although it's just the magnitude that comes into finding the probability of finding the particle at a particular position, the phase does matter. And the other thing to take from this is that these type of experiments led people to think of the wave function as an actual wave. The particle is a wave that extends through space, just like a water wave would be. It's a physical object. So that was the first weird thing about the wave function I'm going to talk about. The second weird thing is measurement. So I've sort of already alluded to this, but let's think of a particular example. Consider an atom that decays. It could be a nuclear decay, or it could be just a photon being emitted, and it emits in all directions. So you get this spherical shell-like wave function coming out of it. So at a particular time, it's going to be, looking at a cross-section, it's going to be a circle. So that's the wave function of the, say, photon being emitted. Now consider putting a detector at a particular point. If you get a click at the detector, then after that point, we think about the wave function as being collapsed or reduced to being this size, just the size of the detector. So the weird thing about this is that if you think of the wave function as a wave, say like a water wave, as an object, then suddenly it's changed instantaneously. So if that circle was very large, then this change could mean you have effects that propagate faster than the speed of light, from one side of the circle to the other. And the other weird thing about it is that this collapse is non-deterministic. It's not described by the Schrodinger equation. In other words, it's probabilistic. So we have these two types of evolution in quantum physics. We have the evolution by the Schrodinger equation, and then we have this measurement process that we don't really know how to describe properly, still to this day. So these type of problems disturbed a lot of the initial thinkers about quantum physics, and they argued back and forth about them at a series of conferences known as the Solvay conferences in Brussels. And this was probably the most important Solvay conference, the 1927 one, at which Einstein and Bohr argued back and forth about what is the meaning of the wave function. So these conferences were pretty amazing. If you look at the list of people down here, they have, I think, 17 Nobel Prize winners in that list. So you can spot them all. There's Einstein, there's Bohr, and looking down the list, there's Lorentz, Bragg, Curie, the only woman.
Does she have this too?
Had two, yeah. She's the only one that had two, and she's the only woman there. So at these conferences, they argued about, the main point of this conference was really to argue about what was the wave function, what was quantum mechanics talking about, what was the meaning of it. And these arguments basically went back and forth between Schrodinger and Einstein. And Einstein took this position, which he describes in this quote, "An inner voice tells me that quantum physics is not yet the real thing. I, at any rate, am convinced that God does not throw dice." So what he meant by that is that he didn't believe that quantum physics was complete. He thought that we were ignorant of some sort of underlying theory that could describe deterministically what happens, say, in measurement instead of probabilistically. And so just to be a little bit more specific about what he meant by that, so we talked about the wave function as being this distribution. Can we think of it as, he said that we could sort of think of it, or he thought we should think of it as a statistical probability distribution, something like that. An example of a statistical probability distribution is if you consider rolling two dice, and then you plot the sum. So what's the probability of getting all the different sums on those two dice? I've just plotted it here. And that's because there's many different configurations that lead to the same sum. So in particular, if you think about probability, about the wave function this way, then suddenly collapse is not disturbing anymore. It's not this instantaneous physical change to the wave function, because as soon as you learn something, as soon as you make a dice roll and you get a particular result, say 5, then your probability distribution collapses to being probability of 100 at 5. So this looks like, in some sense, an instantaneous change, but it's not an unfamiliar one to us. It's just an updating of our knowledge. So in this view of the wave function, collapse no longer becomes weird or non-local or unphysical. And just going back to what Einstein said, if you think about rolling a dice, you're going to get a particular result, but you can predict what that result was. Although to us it's random, because we don't have very good control over our hands when we throw the dice. If you carefully analyze the position, momentum, and angular momentum and the forces on the dice, you could predict on any given roll what the outcome would be. So that's what Einstein meant by wanting a deterministic underlying theory. So Bohr disagreed with this. And he said, Einstein, stop telling God what to do. But Bohr didn't really have a great answer either. He's sort of famously obtuse about this. He said that the wave function is just an abstract object, simply an element of the theory used to make predictions about observations. So this is sort of a very hands-off approach to what does the wave function mean. It's just something we use in our calculations, essentially. And they argued back and forth at the Solvay conference, and these arguments are actually quite interesting because Einstein would come up with situations where he thought that quantum mechanics would be obviously wrong, and then Bohr would show what was wrong with Einstein's thinking. And they came up with these crazy apparatuses that sort of illustrated each one of their points. And I highly encourage you to read about these because they tell you a lot about physics. And in fact, a lot of these have gone on to be implemented, although some of them are still not been achieved in experiments. So this was pretty much philosophy. I mean, Bohr kind of won the debates, and so the Copenhagen view, which he was from Copenhagen, dominated physics for a long time. But to a lot of the people, it was just a matter of philosophy. There was no experiments that really could tell you definitely one or the other view was correct. That was until Bell's theorem. So Bell's theorem, some people think about as being the most profound discovery in science. And I'll show you why in a second. And at the heart of Bell's theorem is this phenomenon in quantum mechanics called entanglement. So that's the third and last weird thing about the wave function that I'm going to describe to you. So Bell's theorem was introduced by this guy, John Stuart Bell, while he was at CERN. That's actually it on the wall behind, on the blackboard behind him, or a modern version of it, and there's the original one. And I'm going to give you the punchline of Bell's theorem first, before describing sort of the physical situation. So first of all, Bell's theorem doesn't really tell us about quantum mechanics in particular, it tells us about nature. So it's a series of measurements that you can do on any system that if you violate a particular inequality with the measurement results, with the statistics of the measurement results, then you can prove that nature is either, or both, non-local or not real. So when I say non-local, it means that things can instantaneously affect other things far away, or not real. So that means that things don't have pre-existing properties that determine the results of measurements. So that the second one is particularly hard to get your head around. And essentially what it means is that, for instance, if you had an apple and it was red or green, you couldn't really say it was red or green before you looked at it. You shouldn't say that. In fact, it wasn't red or green before you looked at it. Or if you don't look at the moon, you don't know whether it's up in the sky or not. The non-local thing is probably a little bit more familiar to people. It just is people don't like it because it seems to violate special relativity, which says that cause and effect cannot be faster than the speed of light. So it implies one or the other of those two things, and possibly both. And the quantum mechanics can violate these inequalities. So experiments on quantum systems can actually produce statistics that violate these inequalities. And in particular, an entangled quantum state can violate the inequalities. So consider an atom that conserves angular momentum in a decay of two particles. So the two particles take away, in total, 0 angular momentum. So that means that they're always pointing in opposite directions, their spins. So I've written their state down here. So one particle is either up, and the other one's down, but that's in the superposition of the other particle being down and the second one being up. The weird thing about the state is that you can write it similarly in every direction. So you don't know which direction they're counterpointing, but they're always counterpointing in opposite directions. It's an interesting state. This is called the singlet state. And it's called an entangled state because there's no way of writing it as the state of one particle times the other particle. So this atom decays and it emits particles that are pointing in opposite directions. And then in Bell's theorem, he talks about doing a variety of measurements on these two particles. And so you can consider what you would get from having a detector that gives you a click only when it's aligned with the particle. Or sorry, not only when it definitely gives you a click when it's aligned with the particle. So you can set your detectors up pointing in different directions, and if it's pointing in the same way as the particle, then it gives you a click. If it's pointing it completely oppositely to the particle, it doesn't give you a click. And if it's at some angle to the particle, well then the result becomes random. That's the probabilistic nature of quantum mechanics coming in. And so the same thing happens there. So the key element of Bell's theorem is that you randomly set the detector directions. You randomly decide what measurements you're going to make. And you need to do this such that these decisions are made out of, and implementation of the decisions are made out of each other's detector's light cone. So that way there's no possibility of information traveling from one detector saying what you set that measurement setting to the other detector and affecting it. So in that case, what you do is you randomly flip a coin, you set your detector directions, and then you get measurement results, and you just build up these statistics. So here they're perfectly anti-correlated. We both get no clicks on both sides at the same time. In this case, again, they're perfectly anti-correlated, so we get clicks on either side. And now we've set them up so they're not, the two detectors are not pointing in opposite directions. So on one side we're going to get a click, on the other side we're going to get complete randomness. So it's easy to come up with a theory underlying physics that would come up with perfect correlations as long as you guarantee that's the only measurements you're ever going to look for. If you guarantee that you're only going to look in opposite directions with the two detectors, then it's easy to come up with a conspiracy theory that will always give you clicks on either side. So for instance, you could have, instead of two particles separating out from the side, you could have two people, and they have pre-agreed that they're just going to give a result based on a particular digit in pi, and then they're just going to cycle through them. So if this guy has an odd digit, then he gives a click, and then if this guy has an odd digit, he doesn't give a click, and so on. So you can arrange perfect correlations in that way, and you can arrange perfect randomness by just sending out random results, or picking random results from your detector. But combining the two is something that local realistic theories can't do. So I'm not going to go through the math, because in my experience, when you introduce Bell's theorem, you usually lose people in the math. But this is what it is. So this is an example of it. And these are just correlations that involve the probabilities of different measurement results. The lesson is that, that nature is not locally real, and because we know that the quantum mechanics predicts that we violate these inequalities, we can say that the wave function is not locally real. So that's the lesson of Bell's theorem that some people think is one of the most important discoveries in physics. So since then, though, that's not the last word in the matter. There's been quite a bit of progress. And I just want to highlight that we're still making progress in understanding these systems. So for instance, in 2011, the same year my paper came out, this paper by Terry Rudolph came out with the title, "The Quantum State Cannot Be Interpreted Statistically." So this is really referring to Einstein's interpretation. And essentially what they were saying is that the probabilistic nature of the wave function is not due to our ignorance of many possible underlying states. So you might think, like for instance in the dice rolls, we don't know exactly what position and angular momentum the dice have in any particular instance, and that's why it has a probabilistic result. It's not due to the ignorance of that kind of thing that we have a wave function. That's not why we have a probabilistic wave function. So you can't, this basically I've just written it pictorially like that. And the second interesting result was that no extension of quantum theory can have improved predictive power. So this is really trying to answer the question is quantum physics complete? Is the wave function complete? And this result proved that if there is an underlying theory, it isn't going to improve on the Born rule. It's not going to let us predict better than the Born rule does. So even if we do discover an underlying theory, it's not going to be very satisfying because it's not going to let us do anything that we can't do now. So that sort of ends my summary of the state of matters in terms of understanding what the wave function, at least in terms of theory. I should say that the Bell's inequalities are being there are some technical loopholes in them, but most people in the field don't feel like those are very fundamental obstacles to the fact that it will be demonstrated as being violated within the next couple of years. So there's two loopholes, the detection loophole and the locality loophole, and they just closed the detection loophole last year actually, in a system in which they expect to be able to close the locality loophole. So now they're working towards that, and it's expected that there will be a loophole-free demonstration within a couple of years. So there is good experimental evidence that we violate Bell's inequalities. So just to summarize, what is the wave function? This is the question that people have been asking in the last century. So Einstein thought that the wave function does not describe a single system. It relates rather to many systems, to an ensemble of systems. Heisenberg said that the wave function represents an observer's knowledge of a system. So this is something I haven't really talked about, but it's actually come back in favor recently, where there are now new interpretations or ways of thinking about the wave function that are just sort of relationships between people's knowledge or beliefs about what's happening in the physical world. So that's an interesting approach that's being explored right now. And then Moore was famously obtuse when he said the state function is purely symbolic, whatever that means. So the Copenhagen interpretation was summarized by Mermin, who you might know from your solid state textbook, Ashcroft and Merman, who summarized it. The Copenhagen interpretation is really due to Bohr and Heisenberg as shut up and calculate. So because I'm an experimentalist, I take a slightly different stance. I say, shut up and measure it. Let's see if we can measure the wave function and come up with a way of thinking about it from those measurements. So there's a problem with this, though. There's something called the no cloning theorem, which is a fundamental theorem in quantum mechanics. And it says that one cannot copy a particle's wave function. And the corollary of that is that it means that it's impossible to determine the arbitrary wave function of a single particle. So the reason why that's a corollary is that if you copied a particle's wave function, if you could determine a particle's wave function, then you know it and you just copy it on, produce another particle with the same wave function, thereby cloning the first particle. So it's a fundamental theorem that says that if we have a single system, in principle, you cannot determine its wave function. So we're always going to be trying to determine the wave function instead, and in my measurement, so I'm going to be trying to determine the wave function of an ensemble of particles that I think I prepared all with the same wave function. So it's still a statistical measurement in some sense. So the quantum system that I'm going to talk about is the transverse wave function of a photon. So we have a photon coming along in this direction, and it has some wave function that describes its position in this direction. And the nice thing about photons is that we can go between position space and momentum space with the Fourier transform lens. So what that means is that the position of the photon in the Fourier transform plane, this gives you the momentum of the photon over here. So we can measure either the momentum or the position just by moving between these two places. And you can see that if you just put a detector here, you could easily measure the probability of the photon being at a particular position. So that's equal to the absolute value, or the probability of the photon being at a particular momentum, which is equal to the Fourier transform of the wave function at a particular momentum. But even if you have those two probability distributions, it's not enough to give you the wave function. That's something known as the 1D phase retrieval problem. You don't see the phase of the wave function in those measurements. That's the problem. And in particular, another way of looking at the problem is that if you make a measurement of position, not by a detector this time, but by a slit, then the light is going to, or whatever particle it is going to diffract out from that slit and give you a completely flat momentum distribution. So now you've made a good measurement of position, but you get no information about momentum afterwards. You can't make a simultaneous measurement of both, just due to the Heisenberg uncertainty relation. Measuring x completely disturbs p. So a question that I had, and that I think most undergrads could have when they're taking a course on quantum mechanics, is why not just measure x gently? If we measure x gently, then we're not going to disturb x, and we're not going to disturb momentum subsequently, and then we can go on and measure momentum, and we can do this simultaneous measurement. So it's sort of a natural question to have, and I assume that if anybody did ask that, they immediately got shot down by their lecturer, because it's not something that people seem to have asked before in the literature. But we did, and so to think about measuring something gently, I'm going to talk to you about a way of thinking about measurement. So I'm going to talk to you about a model of measurement introduced by von Neumann. And in this model, you not only measure the system quantum mechanically, but the measurement apparatus. So in this case, the system is a gas tank, and it's in a superposition of two fuel levels. And our measurement apparatus is a needle, which has a wave function now, that's why it's quantum mechanical, that points to a particular position on a fuel meter, so full to empty. So we model both quantum mechanically, so we're sort of expanding our quantumness of our measurement. And then we interact them with the spring. So this spring drags this pointer along according to where the float is in this gas tank. Is it high or low? And what you find is that it entangles the two. So basically, if this is low, then the pointer is pointing over here, and if it's high, it's pointing over there. But if you measure now your measurement apparatus, this is where we stop being quantum. You're doing classical measurement or a standard measurement on your measurement apparatus. You collapse the pointer to a particular position, and you get a particular result, and you collapse the fuel tank along with it. And if you build up statistics, that sometimes it'll collapse to, if you produce a number of fuel tanks with the same wave function, it'll sometimes collapse to a quarter full, and sometimes collapse to 3/4 full. And on average, it's going to point to the average value of whatever you're measuring. In this case, I call it A. This is called the expectation value. So this is our formula. This is basically the Born rule right here. It's just telling you the average value of the gas tank will point exactly in the middle, the average position in this histogram here. So what's a weak measurement in this von Neumann model? Well, you just make that spring weaker. You make it a weaker spring. So now it's not going to be able to drag this pointer over quite as much. So you have to shrink your fuel gauge. You have to put the markings on it closer together. So I'm going to zoom in so you can see where those markings are. But in the zoomed in scale, the pointer is now wide compared to the markings. And so you can see that on a shot-by-shot basis, we're going to get very little information out. Because even without this measurement, even without this spring here, I could measure my pointer and would have a possibility of giving me every fuel marking on the scale. It extends over all the fuel markings, so now I get very little information on a trial-by-trial basis. The interesting thing is that if you do the measurement and you calculate what the wave function of the pointer does, it actually shifts the wave function rigidly, and it points to exactly where you'd expect it to point, just at the average value of whatever you're measuring. So far, a weak measurement doesn't give you anything good. It just doesn't let you get any information out on a trial-by-trial basis, and it gives you exactly the same average result as a strong measurement. So far, a weak measurement is not interesting. But it leaves the gas tank, because it's a weak measurement and the spring is weak, it doesn't disturb the gas tank. So it leaves it in its wave function. So you can then go on and do normal measurements, strong measurements afterwards. And you could do a strong measurement that gives you a result that corresponds to the state phi. So in that case, the pointer also shifts rigidly, but now it points to a different value. So it doesn't point to the average value of A anymore, the expectation value. It points to this thing that we call the weak value. And the weak value is a very unusual quantity. The first thing to notice about it is that it can be large, because if these are orthogonal states, or if they're pointing in completely opposite directions, then this will be a large number. So that means that this peak can be outside the range that is normally allowed for that pointer. So that's weird by itself. The other weird thing is that this thing can be complex. And that's the part that I'm going to use in my experiment. And what we mean by being complex, because usually measurement results can't be imaginary, is something very simple. It just means that the real part of this you can find as a shift, the position shift of this pointer. But if you look at the momentum shift of this pointer, it turns out that it's also traveling off in some direction. The momentum shift of the pointer is going to give you the imaginary part of this weak value. So the real and imaginary parts of the weak value, the average result of your measurement, are just in the conjugate variables of your pointer. Okay, so that might have been a little bit abstract. So I'm going to go through a specific example now in terms of my experiment. So we have a photon coming along, and it has a particular wave function. And now we're going to measure whether that photon is at a particular x by rotating its polarization by 90 degrees only at that particular x. So they all start out pointing up, and only at that particular position do we rotate them to be orthogonal to that original polarization. So now, if you don't go through that little measurement, that little interaction, then you'll definitely go off to this detector, which only receives photons that are polarized vertically, and we'll be able to say with certainty that the photon was not at that position. And if you go through it, then it'll go to the other detector. So here we have certainty. We can tell whether the photon was at a particular position or not. That's a strong measurement. And if you scan that across and you looked at these results, you would get what we normally get, the absolute square of the wave function. Now you can do a weak measurement just by making that rotation induced by that point, at that point, very small. So now, if a photon travels through it, it only gets rotated a little bit and can go off to either detector. So you don't get very much information on a shot-by-shot basis. So, the interesting thing is that you can now, if you now look, instead of at the vertical and horizontal polarizations, you can also look instead at how much rotation you get. So if you just look at how much rotation you get by looking at the difference between 45 and minus 45, so you get a little bit of a tilt, you're going to get one of those more than the other, then that just gives you the real part of that weak value, which is just, again, nothing interesting, just the absolute wave function squared. The interesting thing is that if we then do a subsequent strong measurement, so here we can do a subsequent strong measurement in the momentum plane, because we have a lens there, just by putting a pinhole in. So if we put a pinhole in, we're only accepting photons with a particular initial momentum, and we only let those photons go off to our detectors. And it's only those photons that we look at the polarization rotations in. So now, the polarization rotation in the linear basis, the difference between these two detectors, gives us the real part of the weak value, the average result of that weak measurement. And now the interesting thing is that in the conjugate basis, just like we had position and momentum for the pointer on the fuel gauge, we have a linear rotation and a circular rotation. And the difference between these circular polarizations in conjugate basis is just equal to the imaginary part of the weak value. So we have these two numbers that we can measure from our experiment by doing a weak measurement. So now I go back to that formula for the weak value, and I consider a particular measurement. We're measuring a projector of x, so that's just the operator for that. We have an unknown initial state, wave function, and then we are measuring a final state of a particular momentum. So I sub all of those into that formula for the weak value, and you get this right here. And if you take, for instance, final momentum equal to 0, then this term just goes to 1. This just goes to the Fourier transform evaluated at 0. So those two things are just constants. And this thing here is just the wave function. So this tells us, the simple math right here, tells us that the average result of our weak measurement of position is just equal to something proportional to the wave function. And of course, we can always get that something out by normalizing the wave function in the end, because wave functions are supposed to be normalized. So what does that look like? Well, it looks like exactly what I just drew. So we have a slit at p equals 0, so exactly along the axis of the system. And we look at the imbalance in the circular polarizations, and that gives us the imaginary part of the wave function, something proportional to that at least. And then the imbalance in the linear basis gives us the real part of the wave function. So that's the idea behind the experiment. So how do we get our photons? Well, we use a process called spontaneous parametric down conversion. So we want to make single photons. We're not particularly good at that. So we have this way of instead making something called heralded photons. We take a very bright pulse with a lot of blue photons in it. We send it into a nonlinear optical crystal. And occasionally one of those blue photons splits into two red photons. The nice thing in about this process is that the photons are always created in pairs. So that if we detect one of those photons, then we know this remaining beam, which is orthogonally polarized, only has a single photon in it. So most of the time we produce nothing, but when we get a click here at the heralding detector, we herald a single photon in the other beam. So that's our way of making photons. Then we send them into an optical fiber, and that initializes their transverse wave function to be the same as that supported by the fiber. So the only photons that get transmitted by the fiber have essentially a Gaussian wave function in the transverse direction. So that's how we start off with an ensemble of particles all with the same wave function. So this is what our experiment looks like. I'm not going to go into too much detail because I'm running, actually I'm not going to go into any detail because I'm running out of time, but for the undergrads, this is what a typical quantum optics experiment looks like. The nice thing about it is that it all fits on one table and you can build it up all yourself. So it's these type of experiments you can do pretty much all of them if you want. So these are what our results look like. So here's a little picture of our fiber with a polarizer in front of it. And then here is a little sliver of quartz that we use to do our polarization rotation. And here's our Fourier transform lens. And these are our results. So here is the real part of the wave function that we measured, and here is the imaginary part of the wave function. So I should say that we collimated the light coming out of the fiber with a lens. We wanted to see a Gaussian wave function, so we wanted a very good lens that wouldn't induce any sort of phase distortions to our wave function. So we were kind of limited in terms of how big a lens we could go to. You just can't buy very good big lenses without spending a lot of money. So we found this lens, but we had to truncate a little bit of our wave function. We lost some of our photons out of our system. So what we expected is a truncated Gaussian here. And we didn't really see it in terms of our real and imaginary components. So we were a little bit confused because we expected to be a flat phase and just have a truncated Gaussian. But then we took the absolute squared. So we took the square of this and added it to the square of that. So that should give us the probability of being at a particular x. And we found that indeed it gave us something that looked very close to a truncated Gaussian. And in fact, if you took a detector and ran it right across this line here, that gives us these black points. and the two agreed very closely. Now if you take the arctan of the ratio of these two, that should give you the phase. And what we found is that the phase actually varied by quite a bit. So that confused us a bit. It sort of said, is our measurement actually working? Because it's giving us this odd phase here. And in particular, this lens was spec'd to only give a 1/100 phase shift. So in the end, we took the lens to a special facility to measure its aberrations. And it turned out that it was much worse. It was exactly what we were seeing here. And it turned out that so we called up the manufacturer and they said, oh, yes, that's the design specification, not the manufacturer specification. And we should really put up the manufacturer specification on the web. So it was a very much over-specified lens. We should have kind of should have known that because it was somewhat fantastic specifications. Okay, so we were finding things out about our system that we didn't even expect to see, really. So then we thought we should try some other wave functions just to make sure that it works. So to stop truncating the photons, we took a reverse bullseye filter so that transmits more in the center than at the edges. And we put that in our beam, so right here. So now we're not truncating it. And this is what we got for the absolute square. So again, it agrees really well with what we get as the detector passes across it. We also then put a glass plate across half of it. So now it's going through some glass material. We should get a phase shift, a discontinuous phase shift right there. And in fact, you see that right in our real and imaginary data. You see it in the phase. And then really nicely, if you take the absolute square of these two imaginary and real parts, and take the square of this and add it to the square of that, you then again get the original wave function again. So although we're changing the phase, we're not changing the magnitude, just like you expected. So then we tried some more interesting phase profiles. We put a tilt on our wave function, which is just like a linear phase gradient across your wave function. We put different tilts, and they agreed well with what we expected in theory. The slopes agreed well with what we expected from theory. And we changed the position of the lens, which gives you a phase curvature across your wave function. And again, we measured that well, pretty well with what we expected from our model. Yep.
What sets the phase reference?
The phase reference is set by the axis of the system, basically. So where you put the p equals 0. It's a good question, though. So with those wave functions that we measured, we decided that our technique was working and that it indeed does measure the wave function. So why do we call it a direct measurement? Because there are other ways of determining the wave function. In particular, there's something called state tomography, in which you essentially invert the Born rule. You just take a whole large arrangement of measurements and you try to take as many as you can in different orientations, and then you invert those measurements and find out the wave function that's most compatible with them. So you sort of do a reconstruction. But that's a very complicated procedure, and it only can reconstruct the whole wave function. It's a global procedure. So one thing that makes this direct is that it's local. We measure it at a particular point, which is something we'd like to do from a direct measurement. Unlike state tomography, there's no complicated mathematical reconstructions. The value of the wave function appears right on our measurement apparatus. So again, we see it as these two different signals. And then finally, the procedure is simple and general. So you can describe it just as measuring x and then p. It's a simultaneous measurement of both. Just that the x is gentle now. And in fact, it's general because you can use any two complementary variables in any system. So another way of looking at this measurement is as an analog to how people resolve their thoughts about electric and magnetic fields when they were introduced. So for a long time, people argued about the reality of electric and magnetic fields. And one of the things that resolved those questions, and we still use in our introductory courses, is the idea of test particles. So particles, where their charge and their mass are taken to 0, will follow the field lines of electric and magnetic fields. So in this case, we have iron filings following the magnetic field lines, and here we have grass seeds following the electric field lines. So in this case, we're trying to find out about the wave function, which tells us not about an effect on charges or dipoles, but an effect on measurements. So we need to have a test measurement, and that's one way of thinking about the sweep measurement. So perhaps it'll be similarly useful for understanding the wave function, as test particles prefer understanding electromagnetic fields. And then secondly, just because we have now a very simple way of measuring the wave function in the lab, it provides what's known as an operational definition. So operational way of thinking about physics was introduced after Einstein came up with special relativity. So people sort of looked at how Einstein came up with special relativity, and they said, we should never really make these mistakes again. We should never come up with assumptions about how time evolves and whether time is passing the same way in different reference frames. And if you think back to how Einstein came up with his ideas, he came up with specific ways of measuring time, and those illustrated, or measuring and synchronizing clocks, and those illustrated some assumptions that we had made about how to measure time, and led to his concepts of general relativity. So the basic idea behind an operational definition is that you want to define something not in terms of concepts and vague words, but in terms of specific actions that you do in the lab. And so this does that. It has a very specific procedure in the lab, and simple procedure in the lab to measure the wave function. You make a weak measurement of a variable, and you follow it by the strong measurement of a complementary variable. And the joint results of those measurements, will give you the wave function. So in this case, we did x and p. So perhaps that'll let us think about the wave function in the future. So this is an undergraduate talk, and so I think it's particularly apt that I should tell you that all of the data in this experiment, and the experiment was mostly built by 3 undergrad students while I was at NRC. This is Corey Stewart. He's now doing a PhD in photonics. This is Alvin Patel. He's now at Southampton, UK, doing a PhD in photonics. And this is Brandon Sutherland. He's also at U of T doing a PhD in photonics. This is my collaborator in this research, Charles Bamber, and our technician, Rick Gerson. So I'll just conclude there, just on time. So just want to leave you with the point that even though asking the question, what is the meaning of the wave function, may seem like a philosophical question, there has been progress made on this over the century. And it may not exactly answer the questions that we wanted to answer, but it answers related questions, and we are finding stuff out about quantum physics. It's not just a philosophical question. And the other thing I want to point out is that the math behind Bell's theorem and a lot of these things is very simple, and behind my experiments is very simple. And that you can understand it at an undergraduate level. So if you go back and read these papers, as long as you have some basic probability theory and some basic quantum mechanics, that means second-year quantum mechanics essentially, and you can understand these papers. And if you come up with questions about your courses, you should try and remember them, because you may come back to them once you become a professor, and they may turn out to be good papers. So, and the final thing I just want to point out is that just to re-emphasize that this direct measurement procedure is not just limited to x and p. It could be any 2 conjugate variables. It could be sx and sy. You can measure spin of an electron, frequency, time, wave function of a photon, or basically any 2 conjugate variables. And then finally, if you're still dissatisfied with your knowledge of the wave function, you can just follow Willis Lamb's advice when he was teaching his class at Columbia, in which he, after writing the psi on the blackboard, he said, don't worry about what this means, you'll get used to it. Thank you.
We have a few minutes for questions. Sir?
You mentioned about the source of single photons, that you're not too good at doing it, actually.
Mm-hmm.
Why is it so difficult to get single photons?
Well, there's two strategies for getting single photons. One is the one I told you about, which is you create them in pairs and then you parallel them. So we are pretty good at that, but it's an indeterministic source, so we can't produce them when we want to. So in that sense, that's why we're not good at that. The other type of source which would produce deterministic photons is if you have a single emitter. And then you excite that single emitter to an excited state, and then it decays and produces a single photon on demand. So in that case, the difficulty is really in creating a single emitter, a good single emitter. So if you think about an atom, you need to have a single atom that's isolated from other atoms, and you only excite that one atom, and then you collect all the light from it. So that's the challenge. So that's an actual challenging thing to do. For instance, you need a vacuum chamber. You need to hold the atom in a particular place. we need to catch the atom in the first place, and then we need to collect all the light that comes out of the atom. These are all challenging experimental facts.
You measure, you perform a weak measurement of one variable followed by a strong measurement of the complementary variable, right?
Yes. Yeah.
But it doesn't seem obvious to me that the results depend on the other. Why don't you? Can you try to make a strong measurement first and then a weak measurement, or
If you did a strong
switch the
measurement,
variables? And
you can switch the variables. So you could do a weak measurement of momentum and then a strong measurement of position. But the order has to be the way I said. It has to be weak then strong.
okay.
So because if you did a strong one first, then you would destroy,
Yes,
all the information about the system.
so it's the variables themselves that can be switched.
The weak measurement, the nice thing about it is that it doesn't collapse the system, is one way of looking at it.
Yeah. Can you go back to your double-slit experiment slide?
Okay. So, right in the beginning.
Yeah, very close to the beginning. Okay, you said that you would get this with a single photon.
Single photon at a time. So not one, you won't get a pattern from one photon. So probably just
So,
spoke.
yeah, the pattern would mean, so a single photon would go somewhere in that screen, right?
Yes. That's right. So if you can't send a single photon through and get this pattern instantaneously. A single photon will lead to a particular spot on that screen. And then, so here I'm showing those spots as you send those photons through, one at a time, slowly building up an interference pattern. The key thing is that you can design an experiment where you know there's only a single particle in the system at a time. And so that's one reason to think that these wave-like properties are not just an ensemble effect.
It's not just a probabilistic thing. It's a probabilistic thing. You get one
That's right.
one
And
dot per photon.
where it lands on the screen is probabilistic, but the fact that you see interference is not probabilistic in a sense. And that's one of the reasons why people were tempted to think of the wave function as a wave, is that it seemed like it was an integral property of the wave function.
So part of this whole, like, you do the weak measurement first and you do strong measurement, to me it feels like you're getting away with something. Like you're getting a little piece of information that doesn't keep you from then doing what I think is a typical measurement, what you're calling strong measurement. So based on the fact that you have committed this crime without getting caught, how many more times could you do that? Could you have multiple different weak measurements and then a strong measurement at the end? Like, could you do a weak measurement at this position, and that position, and that position? And how long before it becomes a strong measurement? How many weeks in one strong?
Well, yeah, so something I kind of glossed over in the talk is that weak value is really only the average value in the limit as the measurement has a strength of 0. So in that limit, you get that average. And as you go away from that limit, the average diverges from that. Although it goes asymptotically, so it goes slowly away from that. You don't need to make it very weak. So how weak you make it will determine how many measurements you can do in a row that will be equivalent to a strong measurement.
Is there any reason why it's better to do 2 weaker measurements than 1
There's lots of reasons.
stronger weak measurement?
There's lots of reasons. So for instance, say you wanted to measure a system and you wanted to get some information from it and then act upon that information to guide the system. So for instance, to steer it, you want to know where it is and then you want to feed back on that information and send it somewhere else. So people use that to try and control quantum systems. It's a very natural thing to do. You don't want, so you end up with this sort of balance between feedback and measurement in these systems. So people talk about using this for controlling errors in quantum computers or steering atomic clouds and shaping their wave functions. So that's one reason why you might want to do successive weak measurements. You also get more information out. So I didn't really say this, but you don't need to do a strong measurement as your second measurement. It could be a weak measurement. And then the correlations between the result of that joint measurement is still going to be the same as what I told you. So you're not restricted to weak measurements. So then you could go on and do another measurement on the system. For instance, it could evolve in time, and you could do some other measurement to find out how it evolves in time.
this approach was, I mean, you propose this approach just to measure phase and amplitude or real animation in front of the wave. Still, you need an ensemble to do these measurements. So you need a set of ensemble. So as far as I understand, you agree with the board rule of the statistical approach of watching wave function. So I think there is no deal with Copenhagen interpretation of quantum mechanics or whatever interpretation of quantum mechanics. You accept that rule, and then you find a way to measure the wave function, the imaginary real part of the wave function. But still, they are based on that rule that you accept. Have you ever think about another way just to overcome the Born rule and watching the system and finding what's the wave function without playing with the interpretation without playing with the Born rule?
Well, okay, so it's hard to see how you could do that, because how do you extract information from a system without relying on the Born rule? The Born rule is what we use to predict the results of measurements. So it's really hard to see how you can get away from the Born rule. In some ways, weak measurement does get a little bit away from the Born rule because it interacts the system with another system. And the exact measurement we're doing now, if you describe it in the Born rule, is something that doesn't look like what you think it would look like. It doesn't look like the position operator that we're originally measuring. That's what interacting it with our pointer does. So in some ways, we're already getting away from the Born rule. But in the end, the combined system of the pointer and the measured system, in our case, polarization and the spatial wave function, the measurement on that will be described by the Born rule. And I don't see any way of getting around that, unless quantum mechanics is wrong, which still could be true.
Yeah, so what is the clear difference between measurement versus operation? So why is it a weak measurement instead of operation to this particle? Do you understand what I mean? Like what?
How is measurement different than just any other operation? Is that what you're asking? Is that what you're asking, or?
Yeah, I'm asking, like, is weak measurement equivalent to just operation without destroying a particle?
Okay, so you can even describe measurement as even normal measurement as an operation on a particle in a sort of expanded, generalized formalism of quantum mechanics, something like we like to use in quantum information. And in that operation, which isn't described by the Schrödinger, it creates something that's known as decoherence. So now, for instance, in our case, if you did a strong measurement, then different positions in the transverse wave function would have no phase relationship relative to each other. So going from something that does have a phase relationship to something that doesn't is an operation that we know how to sort of describe mathematically. So in that sense, all measurement is an operation. And weak measurement just sort of keeps the wave function more described by the Schrödinger equation than by that decoherence that destroys the coherence between the different positions of the wave function. So the short answer is that all measurements are operations, in a sense, including weak measurements. So it doesn't look like I satisfied you with that answer.
I just have to get used to it.
Okay, well, let's thank Jeff again for a great talk. Down in the 146 down there.